last time. I say this is basically a differential equation, right? And this differential equation is the order of 3, right? It's a 3 times differentiation. And of course, this ut can be any function. Can be of any function. Now, last time we teach you by setting x1 equals to y and x2 equals y dot, x3 equals to y double dot. Then, because y dot is x2 and y dot actually is x1 dot, because x1 equals to y, right? So y dot is x1 dot. Similarly, y2 dot, right, is x2, because x2 dot. y2 dot is actually y2 dot here. The y2 dot here is actually x2 dot. So that means x3, we can set x3 equals to y double dot and equals x2 dot, right? Now, through this equation, let's go over to this side. x1, so x1 dot equals x2, right? From this, x1 dot equals x2. And then x2 dot equals x3, right? x2 dot equals x3. However, if we take x3 dot, that becomes y triple dot. Then y triple dot from this equation, moving these terms to the right, it will become y triple dot equals x3 dot equals minus a y double dot minus b y dot minus c y plus ut. And then we remember y double dot here. Y double dot is x3, right? So y double dot is x3. And then similarly, y dot is x2, right? Y dot is x2. And y is x1. So you have this equation, minus a x3, minus b x2, minus c x1 plus ut. And we can write this in this format, matrix, linear algebra, remember? We can write that equation in this linear algebra format. And then it becomes this form. This form. This is what we call state space. State space representation. And then A will be equal to that, B equal to this, because right now U can be FT or UT here. That's the same. So this could be UT. So I maybe need to change that. Let me make a replacement here. So I should change this to UT. So this will be UT here. This will be UT here. Okay? So we call this state space representation. Because this system is still linear. So this matrix becomes like that. And A equals a 3 by 3 matrix. B equals a 3 by 1 matrix. Because U here is single input. If this problem becomes a little bit different, if U can be multiple, here U is only single input. But there are times U can be multiple input, which is fine. You know, if we have another system, we can even have multiple input and multiple output. Okay? But here we just simplify this for U. Only single input, only single output. Okay? But basically, this state space representation can deal with not only single input, single output, can also be useful for multi-input, multi-output variable. Multi-input, multi-output problem. Okay? So that sometimes you call this, you know, single input, single output is called SISO, which means single input, single output. And MIMO means multiple input and multiple output. Now you can imagine if it's multiple input, multiple output, U can be a 3 by 1 vector. U1, U2, U3, right? If it is a U1, U2, U3, 3 by 1 vector, then this vector B would also need to be 3 by 3, right? Right? 3 by 3. And then it would also corresponds to this 3 by 1. Okay? However, right now, because we have only one single input, and this becomes 3 by 1. If U is 3 inputs, then this will be 3 by 3. If U is 2 input, U1, U2, this will be 3 by 2. Right? Does it make sense, right? Likewise, Y, for this case, Y is also a single output. So here, the C is 1 by 3. So 1 by 3 times 3 by 1, that becomes 1 by 1, which is 1, right? But likewise, if you have multiple output, if Y is, let's say, 3 by 1, then here C could be 3 by 3, right? So that's clear. A lot of times D is 0, like in this case, D is 0, because Y has nothing to do with U. In this case, remember we set Y equals to x1. So Y equals x1, that means here, C is 1, 0, 0, because from this equation, 1, 0, 0 times x1, x2, x3, that means Y equals x1, right? Which is that equation, Y equals x1. So in this case, D is 0, C is 1, 0, 0, okay? Now this is the famous state space representation for modeling control. Now the reason we do this, the reason we are moving from this traditional differential equation to this state space is simply because x dot plus ax plus bu. See, this is differential equation. This is not. Y is not differential equation. Y is just matrix operation. But you have to solve this differential equation, right? The top, x dot equals ax plus bu is differential equation. But remember, we can use Euler method, right? We taught you last time, Euler method, to solve this by numerical method, right? So that becomes easy. That's why it becomes easy. Otherwise, solving this equation could be very difficult, okay? And now, this is what I mean. You can solve this equation, this second equation, particularly this equation here. You can solve this by Euler method we teach you last time. And now the basic principle is just very simple like this. X, I plus 1, xi. You know, remember this is xi not x plus 1 minus xi divided by h, right? That's this. X dot equals xi plus 1 minus xi divided by h. Now we move the h to the right hand side, and we also moving this minus xi to the right hand side. So this is the equation. And remember, this is just like we teach you last time. This is the Euler method. H is the step, and phi is the tangency function, the function, right? This is the slope or the tangency function, remember? So same thing here. We put this on the right hand side because ax plus bu is phi. And then h times this phi. And now with this, because it's a vector, so we have x1, x2, x3, remember? x1, x2, x3. So in programming, it will be 3 lines. x1, x2, x3. Now for state space, you can have up to x1, x2, x2, xn. That's fine, right? So writing the program is the same. 3 lines. And you can solve this iteratively, step by step. You can solve this problem iteratively, step by step. Okay? Now, if we look at this equation, if you are to solve it analytically, not by numerical method, but by analytical solution, this is the solution. Okay? It takes time to derive it, so I just give you the solution. I just give the answer. But you can see this one with initial value EAT times this plus integration EAT and BU. You know, this is long equation, and you have to solve it by hand, which is difficult. But by numerical method, this becomes much easier, right? You understand what I'm talking about? 大家知道我在讲什么吗？解这个方程式，就等于解刚才那个微分方程式。我们只是把刚才那个微分方程式转成这个表达式子。那表达式子是这个，因为它马上就可以用我们上堂课所教的流拉法来解它，用数值方法解这个答案，而且是用迭代法，一步一步的写程式迭代它，啪，一步一步一个，每一个 h 就会给你一个答案，你 h 很小没关系，每一个 h 就给你一个答案。然后最后你就可以把整个路径把它画出来，结果画出来。但是如果你不是用数值方法去做，那你就要用传统方法去解它，那这个是标准答案。这个标准答案你可以看到它要积分，很累，很辛苦。Okay? So I'm telling you that numerical method is really powerful, but yet it's still simple. It is simple. Okay? So now let me go back to this. Here with this form, we are letting x1 equals y and x3 equals y dot dot. Now I want to sort of modify a little bit, and you will see why. I'll show you. Instead of using x1 equals to y, now I change it to x3 equals y, and x3 equals y dot, x1 equals to y dot dot. This is just a little bit different. But I will show you why. So if I change this, then you see, because x3 is y, so x3 dot is y dot, right? And x2 dot is y dot dot. And y dot is x2. And y dot dot is x1. And then now x1 dot becomes y triple dot. And again, you can write the right-hand side equation. You know, moving this to the right-hand side, it becomes like this. And it actually becomes minus a x1, minus b x2, minus c x3. And then we can still write this state space. And this state space, you see, the matrix, the A matrix, a little bit different from the previous one. Becomes minus a, minus b, minus c on the top. Let's make a comparison. See, this A matrix here is minus a, minus b, minus c on the top row. But then the previous one is minus c, minus b, minus a at the bottom. Right? See, this is a little bit different, right? Okay? And also, look at the C. C also is different. Because now x3 equals y, so y needs to be equal to x3. So C becomes 0, 0, 1. Previously it was 1, 0, 0, right? Now it becomes 0, 0, 1. Okay? And also the B previously was 0, 0, 1. Here it becomes 1, 0, 0. Okay? Because now we have to match the x3. Because ry, because this equation here is the top row, which is this one, which is this one times this one plus this times ut. Okay? So this one still matches our problem. Okay? Now you would ask me, why do I need to do this? You probably will ask me, why do I need to do this? What's the difference between this one and this one? Actually, they're very similar. They're kind of the same. However, the reason I'm doing this is because I'm preparing for another thing. Let me show you why. Let me show you why. here we are converting this differential equation through Laplace to a block diagram. I assume most of you are graduate students and you already taken the undergraduate course on automatic control, right? So this is not new. This is the old stuff for you guys, right? You should know this, right? So this, remember, we are converting this differential equation to a block diagram, right? Block diagram. And the block diagram input is ut, output is yt. And by doing Laplace transform, ut becomes us, yt becomes ys. And the transfer function, ts, this is the transfer function, right? ts becomes this, 1 over s3, s cubic plus as squared plus bs plus c, right? And this is, by Laplace transform, you get this equation, and ys divided by us equals 1 divided by this, right? So this is Laplace transform. You should remember, and this one is represented as a block diagram. Now, so that means if we are given a block diagram like this, then we can go from here to here, right? You understand? We can go from here to here. Agree? Okay? 这样有个问题，我的意思是说，我们现在做的事情就是说，先秀给大家看说，这个是微分方程，但是你举了Laplace transform以后，它变成这样子。那这个可以用我们这个自动控制里头教过的 block diagram 来代表它。那如果它变成一个 block diagram 的话，那它代表说它一样也是可以转换成 state space，right？ 然后你用 state space， 你就可以用一个拉法去解它，对不对？用数值方法去解它。OK，right？ So you got this, right? Now, if it is a block diagram, which means if we have, I'm going to show you that this can be generalized for many useful applications. Now, we want to generalize this, okay? Because previously, let me show you again. Previously, on the right-hand side is only ut, right? Only ut. Now, on the left-hand, now the next one, the right-hand side, I'm going to have another differential equation here. So instead of only u, now I'm going to have du double dot plus eu dot plus fu. So then this will become the numerator. So this part, after Laplace, becomes the denominator, and this part becomes the numerator, right? You should not have any problem, right? 这个应该没有问题吧？这个不需要证明吧？因为你把两边做 Laplace 的话，假设你把两边都做 Laplace， 对不对？我的意思就是说，如果你把两边都做 Laplace transform， 对不对？然后这边就会跑出来也是一样 ，es 平方加 es 加上 f， 然后这个会跑到分子，这个会跑到分母，因为你的 transfer function 是 y 除以 u， 对不对 ？y 除以 u 就会得到这个 ，OK？ And now with this, if we put let me use a g here, okay? Let's have a g function here. So let's just call it g, okay? Just call it g. And then, if we have a g here, we move this to the right-hand side, we can separate this block diagram to be like this. 所以你可以把它变成是这两个 block diagram 的相乘，对不对？这两个 block diagram 的相乘。那你看看这个部分 u 跟 g 的关系是不是跟前面一样？啊 ，u 跟 g 的关系是不是前面一样？ 所以 u 跟 g 的关系跟前面一样，那是这个部分就可以解决它。u 跟 g 的部分是跟前面一样，但是呢，这边呢，我们看看，将它 ds 平方加 es 加 f 的时候会什么意思 ？Because we have, u and g is just like the previous case, right? So if we use u and g, it's just like this case, right? So now this becomes g, right? So you would have this equation for solving g, right? Right, solving g, right? Now, this is g, but then we have another block to the right. So if this is g, we also have this block, right? So what would happen? See, this one basically means, let me show you. This basically means the s squared g plus ESG plus FG, right? So this would equal to what? Because you have ds squared, and ds squared g means d times g double dot, right? And then g is actually like what we show here, right? G double dot is x1. Remember here? G double dot now becomes x1. And g dot becomes x2, right? So actually, we can write this as g dot plus fg. And because we show you that g double dot actually is x1, so this will become d times x1 and plus e times x2, right? Because x1 is g double dot. Because now this y becomes g, so this is g double dot, and g. So here we have g double dot becomes x1, g dot becomes x2 plus f times x3, right? And that is exactly this, right? So you see, this is d times x1 plus e times x2 plus f times x3, right? So then that means we can take this general form, convert it to a block diagram, and then we can use this state space representation solving by Euler method to get the solution. 就是说，如果你拿到一个这样子的微分方程式，它可以转成这样的一个 transfer function， 然后你这样的一个 block diagram 就可以转换成你的转换成就是看你的 A 矩阵就是这个负 A 负 B 负 C 这样子，这是 A 矩阵，然后你的 C 矩阵就是 D E F， 那你最后就可以把 U 跟 Y 的关系解出来，你就可以用这样来解它了，所以你解这个微分方程是用尤拉解它，然后你最后呢，你的 y 就等于 d e f 乘上它，答案就出来了，就这么简单就这么简单。And then so the reason I'm showing you this is general format because if you say what if on the right hand side. If you say, if I have higher order terms, like for example, if I have, D, E, F, if I have higher order terms like maybe D, let me show you. Okay, so if I have higher order terms, what I mean is this. If I have, maybe I can still use G, don't be confused with the same G here, okay? So if I have U, if I have D, U, double dot, plus E, U, double dot, triple dot and double dot, and plus F, U, dot, and plus G, U. If I have on the right hand side, higher, even higher order differentiation, then that means my block diagram will become like this. ds cubic plus es squared plus fs plus g, right? And then here, this s3 plus as squared plus bs plus c, right? In this situation, look at this. This is s cubic. This is also s cubic, right? What you can do is you can 你们那个学过嘛？就是分子分母的话怎么样？我们这个 d s3次方怎么样？一样，对不对？所以你会把它提到前面来，对不对？也就是说，你可以把它转换为 you can convert this equals sorry you can convert this equals d plus s cubic as squared plus bs plus c, and with lower terms, so that would be something s cubic plus something s plus something, like the rest. So this form will be equal to, 也就是你会把它简化以后，前面跑出来这个是 d 了，就是常数了。那后面这个相似呢，分母还是一样，但是分子呢就会降阶了，它就降到 s 平方跟 s， 当然这个系数要算一下，那就降阶 s 平方 s 这个东西等于。那这个部分呢，不就跟这个一样吗？对不对？所以这个地方只是一个常数项，就跑到等于说，它等于是 u 乘上一个常数项，等于 y 就等于那个常数项乘上 u 加上后面的微分方程式常数项的话就变成一个 game， 变一个放大一个 game 而已。So what I'm saying is that even with higher order terms on the right hand side, you can always simplify to be like this, and making this to be the same with this format. 分母跟分子的关系，分子永远会比分母至少低阶。如果这三次方，你这边一定是 s 平方一降；如果这是 s 次方，这个一定是 s 三次方一降。因为如果它跟它一样高阶项的话，那你就可以把它整理提出来，对不对 ？Okay, so I'm saying this is the general form. This is the general form. E can be 0, E can be 0, and they become just like F, right? This is the general form, all right? You don't need to have higher order, because this one, with higher order, it can be simplified to be with this. So, 分母最高项次是多少？分子就会比它减一，降阶一个阶。那这样的话就会成为这样一个 format。三次方、四次方、五次方都一样 ，OK？ So now you ask me, so good, we have this format, and how can we use it for general or complex problem? 就是说，我们如果现在有这样的一个通用的代表式，那它可以拿来真正帮助我们解决复杂的问题吗？答案是可以的，可以的。We'll show you why. Let me show you why we can use this to solve complex problems. Okay? So first of all, we show you that if we have two blocks like this, but they are put together in series. This is what we call series. So let me write it down. This is called series. Series, okay? And then this guy is called parallel. So in Chinese, this is 串联, this is 并联, right? So if you have two block diagrams like this, put them together, and y will equal to g1, g2, r. So y equals g1, g2, r, because they are in series. In this case, then y over r equals g1, g2, right? So this is like a g. And this g, you can put in here, you can put in here. you can put in here. This is G. This is like a G, okay? So let's put a G here. Let's put a G here. This is G, general G. And it means here, if you have a series, you have a block diagram G1, you have a block diagram G2, put them together in series, that becomes this. And likewise, if it is parallel, then it is G1 plus G2. And so you have y divided by r, you have y divided by r equals G1 plus G2. Okay? This is 串联跟并联 series and parallel. Okay? Now, another situation is feedback. This is what we call feedback. So this is what we call feedback. And for feedback, we know that we have an input here and go through a transfer block here. But then it feeds back here to maybe a sensor and then come back here, subtracting. And this is what we call error. And feedback is very important. It is not only used for feedback control, automatic control. It actually can be used in many, many different applications, even in social science, like economy. Economy, we actually can also use a lot of feedback mechanisms. Okay? And here we know ES error, this is error, equals U minus this, right, from here. But U minus this, but this one is actually G times H. So we see G times, this one is G times H. So US minus G times H ES, right? And then US, because now we put them together, we say US equals 1 plus GHES, okay? And the ES equals this, right? And then we have YS here. YS equals GS times ES. So eventually we have this, right? Okay, let me make a correction. US to GS, this is GS. So let's change this. Let's put this back here. This one, let's take it out. Let me make this as a TS, okay? So this is TS. This is transfer function. So we want to get a total transfer function, and then we can use this Euler method to solve this, right? So here I'm showing you that we can combine this feedback loop, combine this completely, making this total into a TS, right? So this one completely is a TS. This is a TS, right? And the duration is simple. You have learned this in automatic control, right? So at the end, we have YS over US equals TS equals this equation. This equation is, you can use it like a formula, right? GS divided by 1 plus HGS, right? So you should have already learned this in automatic control. So this is kind of like a review. Supposedly should be a review to you, okay? And now, one more thing is sometimes we have feed forward. So we call it feedback. And this is called feed forward. Feed forward, that's feedback, this is feed forward. Because we put a G1 on top here. And this becomes a feed forward, okay? Now, you can solve this equation if you want to do this. Now we say, let's put an x1 here. And y equals G3 times x1, right? And then x1 equals G1R plus G2R, right? G2E, sorry, E is here. So x1 equals G2R and times, sorry, G2 times E. So here x1 means we have this pass and this pass, two pass. So one is G1R, the top pass, and another is G2E, the second pass. But then E equals R minus this. R minus G3X1, right? So E equals R minus Y and equals R minus G3 because Y equals G3X1, right? Okay, I'll give you as a homework to do your own derivation, okay? But I can show you at the end the result. The Y over R is this one. I can also use a very simplified method to do it, but no matter what, I'll let you try this on yourself, okay? And you will see by feed forward, the result actually is G3 times parenthesis G1 plus G2 divided by 1 over G2 G3. So this is feed forward, okay? This is feed forward. So I'm showing you that we know this whole thing. Oh, sorry. We can put this together as df, right? And so y over r is ts here. And now y over r is ts. Okay? So by combining using series, parallel, using feedback, using feed forward, you should be able to solve many complex problems and put them, integrate them together. At the end, you are looking for the output divided by input, and that's the TS. Once you have this TS, it will be higher order function, right? 就是高阶的微分嘛，啊，有分子有分母。但是 after you get TS, you go back. You go back to this and solve the problem numerically. You understand? Okay? And so, in principle, this method can help you to solve robotic movement, machine control problem, because they are all moving, right? So if they're moving, this dynamic equation, okay? They have their inertia, like a robot, they have inertia. And you can formulate the robot movement problem like this. You can formulate the machine tool movement like this. And then you can solve, using numerical method, to solve the robot programming problem, the robot movement dynamic equation problem, using this. Now, I'm going to show you the machine tool problem first. So let me explain. Let's say in control. Remember last time I showed you this, right? We always, in control, we always have to have we always want to have a step response. Why? Do you know why we always want to have a step response? And if we have a first order system, let's say, okay, let me put it down here. So for first order, remember the first order, let me use a different color here. Okay, let me change this because you won't be able to see clearly. Let me use this. First order. First order system, we can always have tau y dot plus y equals k ut. Okay, and tau means time constant. This tau is time constant. K is like an amplification amplitude, right? And then it will rise like this. Remember, this is like 67%, right? 70% rise. And this is kind of like a rise time, right? So this is first order system. And you will always have a step response like this. Okay? And if it is a second order system, let's use a different color. If it is a second order system, then what we have is a different format. And usually what we have is y double dot plus 2 times damping ratio, natural frequency omega n y dot, and plus omega n cubic equals, maybe let's put it here, like amplitude ut here. Okay? And this standard format, second order system, then you will have this equation like that. And the damping ratio, if it is smaller than 0.7, it will be kind of like first order system. But, but if the damping ratio is larger than 0.7, it would act like a first order system. But if the damping ratio is smaller than 0.7, like 0.2 or 0.1, it will jump very high, like that. So that is why it's called damping. The larger the damping, then damping will give you 阻尼嘛, damping. It will give you some like first order system. But if you don't have damping, if you use less damping, then this will jump, go like this, right? Okay, so this is step response. Now, why do we care about step response? Let me show you why. In, let's say, machine tool problem, machine tool movement. Machine tool movement usually have 2-axis or 3-axis or even 5-axis machine, right? 我们在工具机 machine tool 工具机加工里头有2轴的、3轴的，甚至有5轴的工具机 ，right? Remember， 轴向越多，价格越高 ，right? 但是最常用的是3轴工具机 ，so most frequently used machine is 3-axis machine, 3-axis milling machine, machining 加工 machining, okay? And what we can say, we can do. Let's try to use as example. Let's use XY instead of XYZ as example because it's easy to show on the board, right? Okay, so we have machine tool movement in X and Y. Let's say we have X and Y. So this is X and Y. And now, if we want to move our position from one place to another place, let me first use an example like this example. Let me show you an example. If we want to have, what is this? This is the logo, right? Nike logo, right? Nike, 大家知道那个 Nike 东西 right? Nike logo, right? So now here, actually, we want to say cut this logo. Okay? If this is a paper, we want to cut it. So on machine tool, this is like a quick machine tool cutter. Starting from here, let's and then begin to cut. And going here, and cutting back, like here, cutting. And then we take this piece out, right? Cutting. Now, so let's say from here to here is a pass. And from here to here, back here, another pass. We have 2 passes. And for each of these 2 passes, we want to generate the cutting 2 pass. From here to here. So let's say this is pass 1. This is pass 2. Pass 2. And maybe we're moving from here to here, and then coming back from here to here, right? Okay, so when we cut this 2 pass, generate this 2 pass, this is actually a curve. But as a matter of fact, for control purposes, we will dissect this pass into many small linear segments. We will dissect this pass into many small linear segments. 中文就是说，这条是一条曲线啊，但是我们要达到曲线，真正在工具机里头加工的时候，它并不是真正的走曲线，它是会走很多直线的小线段，把这条曲线拆解成很多直线的小线段。So let me magnify, say for example this section. Let's magnify this section here, and let's make it bigger. So it actually, you will see from here we have this. From here we have this segment coming here and going up like this, okay, and like here. So what happened is that we actually will generate many small segments from here to here, from here to here, from here to here, here to here, here to here. They are approximated by the small segment. So this is a curve, originally a curve, but we will generate small linear segment like this. 这些都是直线的线段，小线段。We call it NC segment, linear small NC segment. So let me write it down. Small linear 线性的 segment. And these small segments usually can be represented by a G code called G01. 在工具机加工的时候，它是一个 G01 的直线小线段。So they will go from this point to this point by going linear, straight, linear. Like here, also linear. Here, also linear. They are all linear, straight. So if I take one linear segment, and show you. If I take one linear segment, here from here, to show you. That means we are actually going from here and to here. So in X, we move this distance. In Y, we move this distance. So this is delta X, this is delta Y, and this is what we call delta S. So delta S, like for example, I take this segment, and I make this segment here. So this segment here is a linear segment, 线性的, it's called delta S. And delta S can be separated into delta X and delta Y, right? So that means in moving, let's say from P1 to P2, let's say this is P1 to P2, this is P1 to P2. I'm actually telling my machine to move delta X in X-axis and to move delta Y in Y-axis. Do you understand? So this is my machine. I'm driving this machine, right? And for machine 2, in this case, we have two axes, X-axis and Y-axis. So the machine has two perpendicular axes. And in the X-axis, from here, P1 to P2, I move delta X. And then from P1 to P2, I move also delta Y. 所以它有2个轴，一个轴是在 x 方向，一个轴在 y 方向。在 x 轴的我移动了 delta x 的距离，在 y 轴的我移动了 delta y 的距离。就是工具就有点这么简单。Okay, so simple. It's very simple, easy to understand. And now think about delta x and delta y. Actually, they are step function. So for delta x, you are telling the machine from one point to move to another point. Okay? Then delta y also tells it from one point to move it to another point. That's all. That's what it is doing. Okay? So if we can, let's see, if we have a 2-pass like this. So if we have a 2-pass like this, when I'm moving from my position to this position, I just keep telling my system to continuously moving x from here to here, from here to here, from here. So the x movement is from here, continuous movement. Let me show you. For delta x, so I'm moving here from here. Delta x is moving here, moving here, moving here, moving here, and moving here, and moving here, and moving here, and moving here. But my y, delta y, is actually sometimes moving down, right? From here, delta y moving down, and moving down, and moving down, right? Like here. But then I move back, move back, move back, move back. So eventually I move it back here. So they are moving at the same time. 对 x 来讲，它 move 到这里的时候 ，y 就掉到这里来；然后对 x 掉到这里来的时候，它又掉到更低；然后 x 掉到这里来的时候，掉到最低，差不多这里。然后呢，开始回头的时候 ，x 还是往前跑 ，y 呢就开始往后跑，往回跑，往回跑。然后最后 x 跑到这里的时候 ，y 呢就跑到这里来。Right? So for each movement, you are always only need to worry or consider about moving delta x and delta y as a step function. That's all you need to worry about, right? So that means you can solve your system, no matter if it's first order, second order, or even higher order. Higher order may be different, right? May be different. But you are always trying to generate the step response. 我的意思就是说，当你的一个系统 So if this is a system, it's a machine-tool system. Remember, the machine-tool system is like a TS, right? And then TS could be a first-order system, could be a second-order system, could be also higher-order system. If it is higher-order system, we are still using this as transfer function, right? So, like here. Remember, like a general higher order system, TS, like this. This could be your machine tool. This could be your robots. This could have 2 axes or 3 axes or multiple axes, right? You can have multiple axes, right? 多轴都可以, okay? Then you use this to simulate this process. Even for higher order system, you can still generate the step response. And knowing, you will know where the position is at that point. Okay? So we can use this to simulate the machine tool movement or simulate a robot movement. Okay? Do you understand what I'm talking about? 我们今天就不下课，我们就赶快把它讲完。我大概12点就下课，因为西上12点西午有一个西上人会所以我们今天大概差不多讲完，也差不多2个小时就可以讲完所以如果你需要上厕所，你去上厕所，然后会换电脑、秀程式Okay, so we will not have break. We will continue this until maybe 12 o'clock. Okay, because the department has a meeting at 12 o'clock. So, but I think we should be able to finish this by 12, okay? And I'll give you a homework assignment, okay? I will give you a homework assignment, okay? So now you should understand we can represent any function and any system. We can represent any system, even higher order system like PS. And we can use the input. We can generate the input based on the 2-pass or a 2-axis system like this. If we are to simulate a machine tool movement like this, right? 如果要去模拟这个工具机2轴或3轴的运动的时候，那我们现在这个路径呢，它的每一个小段的路径都可以拆解成 delta s。delta s 可以拆解成在 x 轴跟方向 y 轴方向 delta x delta y， 所以你就不断的给它命令啊。那你每次给它命令的时候，其实都是给它一个 step function。那这个 step function 可能长可能短，对不对 ？delta x 可能大可能小，每次都给它一个位置，然后你就会用刚刚的 ts 这个来产生它的模拟，来得到它的位置。You can so what I'm saying is that you can use this ts to represent your machine tool, and you can use the 2-pass to generate from here x0, x1, x2. x3, x3, you know, all the inputs. You know, likewise, y0, y1, y2, y3. Use them as input and put into the Euler method for the solution. So you can put this input, delta x, delta y, and continuously x1, x1, x2, x3, into the ut. You can put into the U side, UT side, U side, UT as your input. And then you can do this you can solve this by Euler method and get your y is your output. P1 P2 不是 P1 不是 input P2 不是 output 哦，不是哦。P1 到 P2 减 P1 是 delta x 跟 delta y， 那个才是 input。delta x 跟 delta y 是 input。delta x 跟 delta y 是 input。Yeah. So let me explain maybe more detail here. Student asked this question. What's the input of this 2-pass? As a matter of fact, as I explained to you, let me show you another picture here. So if I have a 2-pass like this, and I want to go from this point to this point, go from here to here to here and to here. Okay? So you see, I have, for example, here P1, this is P1, this is P2, this is P3, P4, and P5, and P6. Okay? P1, P2, P3, P4, P5, P6. And this is X, and this is Y. So I have two X's. One is axis, Y, X. The other one is Y axis, right? And let's take a look at the P1 and the P2. So starting from here, this is X1, this is X2, X3, X4, okay? And likewise, from here to here, this is Y1, and Y2, and Y3, and Y4. Okay, if we look at X1 only, that means at time t0, I'm at X1 position. And I need to move to X2 position, right? But when I move from X1 to X2, this is like a delta X1, right? Right? And delta X1 means the step function. It means if here I am at, okay, if I use this like a step function, this is like a t here, okay? So this is T0, and this is T1, right? And this is T2, and this is X, okay? That means in here, I am X1. I'm here at X1. But at T1, I move to X2. So that means I have a step function. I want to use a different color to show that. That means I have a step function from here, X1. I need to move to X2 here. But maybe my trajectory is something like this. Or even this. Do you understand? So this is the step function we just showed you. Look at this one. Look at this chart. T0, T1, T2, time, and X is just like this. Just like this. This is T, this is X or Y. So we can say this is T, time, and this is X or Y. Okay? So we are moving from a particular point to another step. So that means when you are moving at T0, you are in X1 position. At T0, you are in X1 position. Now this is T2. You want to move to X2 position. You want to move to X2 position. But T2, you expect it to go like this. You expect this to go like this, like a step function, but it will not, because it's a dynamic system. So you actually move like this until it saturates here. But now at T1, you receive another command to go even further. So here, even before you saturate, from this position, you are going from T1 to T2, you are actually asked to move to X3 position. So let's say X3 is here. So that means we want to go to, at T2, we want to go to X3. But in fact, your path will do like something like this until it hits X3. So your system dynamics will not immediately go to X3. Your goal is, your target is going to X3, but actually it will go like this until it hits X3. Okay? So likewise, this is X and this time. It can also be Y. It can also be Y. So this one can also be Y, Y1, Y2, Y3. Sometimes it go up, sometimes it go down, right? Okay? And then you combine them together. You combine them together. When you draw the XY motion, you will bring them together. So when you draw them together, you draw X, you draw Y, and you put them together in 2D XY, and it will become. And you will actually move from here to here, from here to here, from here to here, and moving, going up like this, and going back. Okay? So this is the principle of applying this to our XY machine table. XY machine table movement. Actually, it's quite simple. If you understand it clearly. 你如果了解的话，其实很简单的，非常简单。Okay? It's actually all step function. Okay? Okay. So now, so I'm going to show you the program. Last time I showed you already. Today I'm going to get into more detail to show you what happened. Okay. So let me do this first. So for automatic control, let's say we have a system. And we have a feedback. let's say it's a unit feedback. And so here, let's say if we have U or R, this is U, okay? And this is Y. U or R usually means the input. And this is, for example, a G function. And this is a controller. And for the controller, right now, let's assume we have a K gain, K amplification. K 就是一个放大的倍率 okay? And this is the feedback loop. What happened is that we know we can use the previous one we taught here, right? This function here, this formula to represent the feedback, right? So we know that for this transfer function, the total transfer function will be equal to 1 plus kg, and this is kg, okay? So this is according to this, right? According to this, okay? So if we have kg over 1 plus kg, now k actually, there is an effect for automatic control if you still remember when you're learning automatic control. Number one, with feedback loop, we will shorten the transition time. Okay? So with this feedback, we'll move the step response faster. That means if GS is a second order system, let's assume GS is a second order system. For this step response, originally you want your, let's say you want your system to have a step response like this. You always want it to respond fast. You always want this to respond fast like this, right? But it will not. GS, if it is a first order or second order system, it actually usually will move very slowly like this. Right? Something like this. But now with feedback control and with a K gain, we actually can have faster response. Okay, let me just use this chart. Same thing. With feedback and with K gain, we actually can have better performance like this. We can have better performance. Now, if it is the first order system or second order system, they may be a little bit different. Okay? What I'm showing here is the second order system. Okay? With this red curve, it's a second order system. And we want to control that so that it rises faster, shorten the response time. Okay? So this is the advantage of using feedback control. You understand? Okay? So when we are controlling the machine tool or controlling the robot, we will always try to use feedback control to increase this response time, increase the speed, and also increase the accuracy of the two paths. Okay. So with this, I'm going to show you the program again. Okay. If you want to go to the restroom, that's fine, okay? Okay, last time I showed you this. Let me do this again. Showing the example. You will see now I have a. Let me use the board to show you what I'm trying to do now. I take one example from a textbook like this, and I'm going to show you. So now I have a system, let's say a second order system, okay? So if I have a second order system like this, this is the K gain, and this is the system to be controlled, which is 1 over S plus, this is 1, and this is 10. And assuming the sensor is 1, coming back, let's say the H sensor is 1, right? And you have input this UT here, and this is your output YT here. We want to see the step response, right, of this K value. If open loop, now this is S plus 1, S plus 10. Okay? So you actually, this is what we call GS here. Let's say GS, right? And we know that our output should be Y over GU or YS over US should be equal to KG 1 plus KG, right? But we have this G function equals S times S squared plus 11S plus 10. Or it can be written as 1 S cubic plus 11S squared plus 10S plus 0, right? So this is our GS. This is our GS, right? Okay? Then, let's take this function here. I will use G1 to input this GS, which is that GS. Okay, I'll input that. And I'll do a feedback, G feedback 1.0. 1.0 means the HS here. This originally there's a HS, right? But now HS, let's assume equal to 1, right? And then we will generate the output, and we'll take a look at the step response for 5 seconds. Okay, we'll take a look at the step response for 5 seconds. Okay, and the step response, as I explained, you're just using Euler equation, Euler method. You can solve the solution, right? Step response. 你可以用教过的那个流拉法，对不对？来解 step response. Okay. So let's see. Let's take a look at this one. So the program asked me to enter the degree of the denominator, and then we see the denominator 分母 is s3 次方加 11s 平方加 10s 加上 0. So we know the order is 3, right? We have 三阶 3. The order, the degree is 3, right? So let's enter 3, and then enter the coefficients. We have 1, 11, 10, and 0. So let's start with 1, and 11, 10, and 0. Then they asked me to enter the degree of the numerator. And the numerator 分子 degree 是0，因为它是常数。常数，但是我们后面会再乘上一个 k， 对不对？还会乘上一个 k。So the numerator is actually k. This actually is k, right? Because gs is 1, but then it will times a kg. Now in the beginning, let's just assume, based on the textbook, we will change the k value. Okay? Based on the textbook, we'll change the k value. So in the beginning, we probably just use 1. Okay, so let me just use 1. And let's see how that result goes. Okay? So let's say denominator degree is 1 because we have degree 3210, and now this degree is 0. And the value, the k value, enter the coefficient because we can use k here. The k value, let's just use 1 now. Okay? Let's just use 1. And then, so we will generate this transfer function. Remember the TS, the transfer function. So the transfer function this, and then we convert it to the, let me make it, so you see, this is the transfer function. And we take the transfer function, convert it to state space representation, remember? And this is the A, the matrix A of the state space representation, right? And this is the B, and this is the C. Remember ABC? So we take TS, transfer function, convert it into ABC. We don't need D. D is 0, remember? And all we need is ABC, and now we have the state space representation. We can use Euler method to solve this, right? Remember? 刚刚教过了哈，就是说你先得到 transfer function，transfer function 就是用这个得到的 ，transfer function 用这个得到的 ，OK？ 然后有了 transfer function， 我们就把它转成 state space，ax 加 b 加，你看 x 到等于 ax 加 bu， 然后 y 等于 c，x 加 du， 那你的 a 就出来了，对不对？你的那个你就可以用尤拉法来解它了 ，right？So now you have A matrix, you can use Euler method to do the simulation to solve your problem, right? And then we actually can find eigenvalues if you want. But now let's take a look. You see, it's even out of the picture here. It's because it's very, very slow. When we set our k value to 1, it actually very, very low here. 它的反应速度很慢啊 ，k 很小的时候。反应速度很慢 ，OK？ And let's try a different value of k again. Now we'll enlarge it to be like 5, okay? So according to the textbook, when k reaches 5 value, it actually be higher. And actually we can also change this to be like 10 seconds, okay? Because right now 5 is a little bit too small. Let's change the next response in 10 seconds. And now we will increase the k value from 1 to 5 or 10. Okay? So let me do it again. And then let me check the k value. The most appropriate value here. Let's start from 5 first. Okay? So now if we change it to 5, and again, the degree, the denominator is 3. And this is 1, 11, 10, and 0. And the top. Now we use degree 0 and then put the k value of 5. Now we use k value as 5. And to generate the matrix again, now let's do the simulation. So now you see, it comes up here, right? So it comes up here. So now it comes up here, okay? This is your step. Now it comes up to the step we want, higher like this. It was here, lower here, right? Now let's do it again and change the k value to 10 or 20. Let's do it by 10. So again, the degree now let's change to 10. You see, it jumps up because this is like a second order system, right? So when the k value gets higher, the response time is shorter. k 值变大 ，response time 快，但是它的 overshoot 也变大 ，overshoot 变大，来。Likewise, let's do it again. Let's go to 20. See how we go. Let's make it drastic again. 再把 k 值变大到20，刚才从5、10，现在到20。So 3, 1, 11, 10, 0, and 0. Now this time we put 20. The k value as 20. So we'll see it should rise faster, but then the oscillation or the overshoot is even bigger. Yeah, so you see here it gets higher. This time, response time faster. It gets higher and we jump like this. Okay? So you are actually, you can tune the control parameters like this. K value, okay? Okay, so we're showing so now we are showing we can use a program to simulate this, right? And this one, what if this is actually a machine tool axis? So let's say if we can simplify a machine tool problem and simplify the machine table axis. So you have a machine tool like this, okay? And then you have, say, the table is here. And this is your ball screw. This is another ball screw. And here also is a ball screw. So, so this is a machine table. You're moving the screw, ball screw, using your motor here, and using your motor here. So this is a motor. This is also a motor. And so what you do is you rotate the motor and you will move in X direction. And when you rotate the motor here, you'll move in Y direction, right? And we can approximate this motor axis, X-axis, Y-axis as a control feedback. And now this controller, we will change it, let's say, sometimes we will not use this simple controller. This you should usually want for GCS, right? And GCS, if it is a PID controller, if you remember, then this will be KP, which is proportional gain, times KI divided by S. That's an integral gain. It will make the steady state error to be 0, and plus a, what we call KD. What do you call it? KD. Yeah, PID, differential gain, right? So that's KD. And this is KDS. So what you need is that you can tune your KD just like I did. You can tune your KD, you tune your KI, you tune your KD. These are all the parameters that you can control. And you put it here, right? And you combine this GS with this is the dynamics of your motor and axis. So for example, this is the dynamics of your dynamics model of your motor and axis. And then you can use a feedback control to simulate your X movement and Y movement, right? And so with that, I'm going to show you what I did last time. Last time, I showed you that I can use this to generate let me take this up. Right now, I don't need this anymore, so I can block it here. Okay, so I'm going to run this program with a machine tool model with x-axis and y-axis. Okay. Also, a complicated model, but that we can simplify it to be just like the one on the board. Okay. So now I choose PC-based controller or Atlanta system controller. I can choose anyone. Let me choose one. Okay. Let me choose one. So that's a PC-based controller. And the PC-based controller, I have a transfer function like this. I have a transfer function. This is a more complicated. If I give you a homework assignment, I'll give you a simple one. Simple one. Not as complicated as this one. Okay? But this is reality. This is real system. Okay? Real problem, real system. So for me, that transfer function is to the power of 3 cubic. 三阶的 third order, higher order, third order transfer function. Okay? And now again, no matter what, but this system, still, it is a TS, right? And with numerator, with denominator, right? 分母分子都有 right? 对不对？但是我们还是可以用我们刚才讲的那个 TS 去解它嘛，对不对？我们刚才有个公式。Okay, so with this transfer function, we will solve the problem. So now you see the step response. So this is the step response of the system. Okay, this is the step response. It's a little bit overshoot. Okay, but then it died down and the accuracy is good, right? Okay, then we draw. Let me show you a feed rate. So right now, if I set the feed rate to be like 300. Then I simulate a car. So right now, I simulate this car. The red color is the original trajectory. 这个红色的就是我们要，比如说像刚才那个 Nike 的勾勾一样，我们要叫这台机器呢，我们要叫我们的工具机从这个位置走加工，跑来这边加工，跑来这边加工，跑上去，跑下来，跑一个路径加工的。但是因为我现在的运动的速度比较慢，所以呢，我们会看到它加工出来的精度还不错，因为呢，它会跟原来的路线差不多。So the red color is the original two pass. We want to generate a cutting pass like this. Now, when I had the machine dynamics, you will notice the blue one at this corner side is actually a little bit deviating from the original two paths because we have what we call dynamic delay. Okay, dynamic delay. So you will see that it will not follow the original path. 意思就是说，在动态的问题里头，当我们的速度跑越快的时候，那它的误差就会越大，但如果我们的速度跑得比较慢的时候，它的误差就会越小。OK， 误差就会越小。So now if I increase velocity, the dynamic error will be even bigger. So let's do it again, but this time my velocity I will set higher value rather than 200 millimeter per minute. Now I will set it like 1,000, 5 times higher. And you will see the two paths gets a little more distorted. I will show you. So now I'm going to enter the feed rate, but now this time I'm going to enter 1,000, which is higher. Feed rate becomes higher. Then the original two path goes faster. You know, 因为速度变快了，我们跑得比较快。Okay, faster. And now take a look. You see here, the blue color, because of the dynamic delay, this time x and y axis do not match well, and then they do not follow the original path. It becomes like overshooting here. Here is overshooting. Here is also overshooting, and come back here because we have overshooting. Remember? So when we have faster speed, the machine
accuracy becomes poor， 加工的精度就降低了。但是大家想想看，这是一个吊诡的事情。If you are a manufacturing person, you go to say TSMC, or you go to Foxconn to work. You are an engineer, and they want to cut this, and they want to cut every day 1 million pieces. So you need to cut it very fast. But when you cut it fast, what happens? Big error, right? Oh, okay, I'm going to reduce it. So I reduce it, and your boss comes to shout at you, say, today I need 1 million. How come you give me only 5,000? 懂我意思吗？因为你切得太慢了 ，OK？ 切得太慢了，因为它的速度太慢。So it's a dilemma. It's a dilemma. On one hand, you want to increase your accuracy. On the other hand, you also want your speed to be faster. But they are conflicting. They're conflicting, right? So you need to maybe do a better control, or maybe to do some other things to modify the two paths. Okay? So that's more advanced. So we don't need to worry about that. I'm just going to show you that by doing this, solving this numerically, we actually can review the problem. We can review the problem, and then we worry about later how to solve the problem. But this is already a very important application to show you that dynamic systems, they do have errors. Okay? And if you move faster, they have bigger error. Okay? So here I will temporarily stop here. We will give you a homework assignment, and the homework assignment will be something like this. Maybe 2 parts problem. Okay, so right now this homework assignment is here. Homework assignment 5, right? Page number 5. So we will have 2 parts. A and B. Okay, A and B. Okay. So the first part, A part, is simple. A part is very simple. You just do what I did today, here, with this. So if I give you a GS like this, right, and you write a program by your own, don't ask AI for help, okay? Don't ask ChatGPT for help, okay? Because if ChatGPT helps you, everybody will give me the same, right? And I know, oh, you guys are, ChatGPT students, okay? You don't need to come to this class, all right? Okay? ChatGPT is like a cheating person, right? So you don't want to do that, right? Okay, so try to do it by yourself because that's what you learn, okay? So the first A problem is to repeat what I showed you today. And you can change the K value, right? K value here, okay? And this is your GS, okay? And then try K equals 5, K equals 10, and K equals 20. Just like I did today. And run the step response, okay? Run the step response. Run the step response, just like I showed you today. Would that be okay? That should be simple. Problem A should be simple, okay? And you are solving the step response by Euler method, which I showed you already. Okay? You can use Euler method, or if you want to use Range-Kutta, that would be great. Range-Kutta is a little bit more advanced, remember? Okay? So you can use Range-Kutta, or you want to use Euler method, that's fine. Okay? Solve this problem by A first, okay? Then the second problem will be doing what I did also with this kind of problem, right? Okay? But I will only ask you to do not like a car, like I showed you here, a car that's a little bit more difficult. But we will give you, I will ask 助教 to give you like a shape, like a triangle maybe, like a triangle, Okay? And triangle has 3 points, right? Then we need to move in x and y direction, right? So if we move from here to here, from here to here, from here to here, with different moving velocity, then you will show that this one may be overshooting, like I showed you today, right? They will not follow exactly on 2 paths. They will have dynamic error. Okay? So the B problem, I will ask my 助教 assistant to give you those values later. And then you'll be able to solve it. Okay? But you can work on first problem first, because I already give you all these numbers. S plus 1, S plus 10, that's a GS. And it's a feedback. And then K is 5, 10, 20. And you don't need to do this parts. Okay? You only do K, which is proportional control. You don't have to do higher, more difficult control, PID control. Okay? Let's just do proportional control. Okay? And this is the problem A. You can get started. And then the later problem, when Zhujiao give you those P1, P2, P3 coordinates, then you can also work on these problems. And we will hand in this report, this homework assignment. Today is December 9th, right? So let's take 2 weeks. Okay, 2 weeks. So that will be 14 days later. That will be December 23rd. Okay, 2 weeks from now. Okay. Okay, and so one more thing before we end the class is that there is something I still need to give you more information so that you can work on problem B. That is okay, to work on problem B, we will need to, let me, right here, I think I can, what's this one? Okay, to work on problem B, I need to tell you something a little bit more. Now, when we move from one point to another point, like P1 to P2, we move from P1 to P2. As a matter of fact, the inside is actually moving small. Remember, even though this is straight line, but in fact, we are still, controller actually still moving in small linear segment. Remember I said that? They are moving in small delta s, small delta s, small delta s, small delta s. They are moving in very small, tiny segment. The controller, the machine, the XY table. They are not like P1 to P2. No, they are moving small linear segment. Okay? So it doesn't matter whether it's straight line or curve. You know, like a Nike hook. You know, like a Nike hook. That still, you can divide it into very small delta s. Remember I said? And every time delta s is decomposed into delta x and delta y, right? So this delta s is decomposed into delta x and delta y. Right? Remember that? Right? Okay, so this process is what we call interpolation in machine tool industry. This is what we call interpolation. 工具机这个也是叫做 interpolation. Interpolation. Okay? Interpolation means that for machine tool controller, they will have a sampling time. Because if you have a trajectory like this, go from here to here to here to here to here. Now notice, originally this is a curve, right? But actually, for machine tool, we can only go straight lines, right? So actually, in machine tool, we actually go straight line. But when you make this line very, very small, and you want to approximate your curve, right? Right? Now, every time you move from one point to another point, from this point to this point, then there is a so-called delta t time. Delta t is what we call sampling time. So delta t sometimes can be written like a big capital T is sampling time. In machine tool, this is what we call sampling time. Okay? So it's just like a discrete system. From analog, this is like analog, to discrete, you have sampling time. Small segment, small interval sampling time. Okay? This is an important concept. It's not just for this, for many things, for discrete time. For discrete time system, we also have this delta t, right? Remember? Sampling time. Okay, so if we have a sampling time, we need to calculate delta s based on sampling time and velocity. Right? So, to make it very, very simple for you, actually it could be more complicated, but let's just make it very simple for you. We know the concept that delta s, what is delta s? It's the moving distance from here to here, right? Or from here to here. This is called delta s, right? So delta s will be equal to what? No. The delta s is just the distance from here to here. Yeah. Yes. Correct. So we actually have velocity times the sampling time, or the delta t, right? So this is the velocity. This is the sampling time, right? So that means, if you notice that in my program, in my software program, the program will ask me, what is your velocity? What is your moving velocity? If I give it very fast velocity, it actually has, big errors, remember? Okay? So delta s equals velocity times the sampling time. And the sampling time is usually fixed for a machine tool, for the controller. The sampling time t is usually fixed. So in this problem, we can let t equals 0.005, okay, second. Or sometimes it's 0.01. So let's just use